Statistics Week 8, confidence intervals. This week we're going to talk about what confidence intervals are and how we can apply them. By the end of this chapter, you should be able to calculate and interpret confidence intervals for estimating a population mean and a population proportion, interpret the student's t probability distribution as sample size changes, discriminate between problems applying the normal and student's t distributions, and calculate the sample size required to estimate a population mean and a population proportion given the desired confidence level and a margin of error. Well, introducing the concept of confidence interval to begin with, there's a motivation for this. We're going to use sample data to make generalizations about an unknown population. This part of statistics is what we talked about before and mentioned called inferential statistics. The sample data help us to make an estimate of a population parameter. We realize that the point estimate is most likely not the exact value of the population parameter, but close to it. After calculating point estimates, we construct interval estimates called confidence intervals. So a point estimate could be an estimate based on your sample of the actual mean or standard deviation or some other parameter, but it is based on using sample data. So essentially it's your sample mean or sample standard deviation as an estimate for the population mean or population standard deviation, which are unknown. Here's an example. The marketing department of an entertainment company is interested in the mean number of songs a consumer downloads a month from iTunes. They conduct a survey and calculate the sample mean x bar and the sample standard deviation s. We're going to use x bar to estimate the population mean and s to estimate the population standard deviation. So the sample mean x bar is the point estimate for the population mean mu, which is probably unknown. The sample standard deviation s would be the point estimate for the population standard deviation, which may be unknown. Each of x bar and s is called a statistic, and that goes back to what we talked about during week 2. A confidence interval is another type of estimate, but instead of being just one number, it is an interval of numbers, essentially a range. It provides a range of reasonable values in which we expect the population parameter to fall. There is no guarantee that a confidence interval does capture this parameter, but there is a predictable probability of success. Here's an example. Suppose for the iTunes example, we do not know the population mean mu, but we do know that the population standard deviation is sigma equals 1, and that our sample size is 100. So those are two dead giveaways right there for this type of problem. You'll know a population standard deviation, and you will know a sample size. Then, by the central limit theorem from chapter 7, the standard deviation for the sample mean is sigma of x bar equals sigma over the square root of n, which in this case is 1 over the square root of 100, or 0.1. Now, the empirical rule, which applies to bell-shaped distributions, mainly the normal distribution, and also one we'll talk about called the student's t distribution, says that in approximately 95% of the samples, the sample mean x bar will be within 2 standard deviations of the population mean mu. For the iTunes example, 2 standard deviations is 2 times 0.1, which is 0.2. The sample mean x bar is likely to be within 0.2 units of mu. Another example, suppose that, for the iTunes example, we do not know the population mean mu, but we do know the population standard deviation sigma equals 1, and our sample size is 100. Same example. Because x bar is within 0.2 units of mu, which is unknown, then mu is likely to be within 0.2 units of x bar in 95% of the samples. In other words, mu is between x minus 0.2 and x bar plus 0.2 in 95% of the samples. Essentially what we're looking to do with this is we're saying we have a sample mean from our sample of, in this case, 100 samples, and what we want to do is estimate or get a boundary for where the actual mean may fall with 95% probability. There's still a 5% probability that it may fall outside of that. So in this example, suppose that a sample produced a sample mean of x bar equals 2. Then the unknown population mean, mu, would be between x bar minus 0.2, which is 1.8, and x bar plus 0.2, which is 2.2. We say that we are 95% confident that the unknown population mean, number of songs downloaded from iTunes per month, is between 1.8 and 2.2. The 95% confidence interval is 1.8 to 2.2. So this isn't a point, as in graphing. This is an interval, as in it goes from 1.8 all the way up to 2.2.